My name is Joseph Wolfenden. I'm going to be giving a lecture on distributed loading. So here we have a distributed load over a rectangular object, or this is a uniform distributed load. So the way we're going to find the resultant force is we're going to take this distance right here of 5 meters. We're going to take that 1/2 times the distance. So that's going to give us 5/2, or 2.5. Next thing we're going to do is we're going to find the resultant force. So we're going to take the 8 kilonewton force from up here and multiply that by the length. So that's 8 times 5, and that's going to give us 40 kilonewtons. So the resultant force is going to be right in the middle at 2.5 meters, and that's going to be 40 kilonewtons. So not too bad for that one. Then we're going to move on to a triangular load. So these ones are a little bit more involved. So we have a load starting here, going to here. This one starts at 0, of 3 meters long, and 2 kilonewtons per meter. So what we're going to do to find the resultant force is we're going to take the length and multiply that by 2/3. So that's going to give us 2 meters right here. So that's where it's going to be acting. And then to find the force, we're going to do the same thing as before, 2 kilonewtons per meter times 3 meters. It's going to give us 6 kilonewtons. The thing we add is multiply that 6 kilonewtons by 2/3, and that's going to give us 4 kilonewtons. So right here at 2 meters from this point right over here is going to be a force of 4 kilonewtons acting downwards. Okay, and here's the example problem we have. So we have a beam with a point A and a force B, that's the unknown over here. So we're going to have to find out what this force has to be in order for this object to be in static equilibrium. So the total length is 5 meters. And first of all, what we're going to do is we're going to find the resultant force right here. So we're going to do the same thing as before on the triangle. We're going to take the 3 kilonewtons per meter and multiply it by the 4 meters over here. So that's going to give us 12. And then once we multiply that 12 by 2/3, we're going to get 24 over 3 kilonewtons, or 8 kilonewtons. And then what we're going to do is we're going to take the 4 meters and multiply that by 2/3 to give us 8/3 meters. And that's going to be 8/3 from over here. So that's where our force is going to be acting. And that's going to be 4/3 from A. It's 4/3 meters. So next thing we're going to do is we're going to find the moment about point A. This is going to be the resultant force that we just got. That's going to be that 8 kilonewtons. And multiply that by the 4/3 distance from A. And subtract that from force of B. That's going to be a distance of 5 meters. So we get 8 kilonewtons times 4/3 meters is equal to force of B times the 5 meters. In the end, that's going to give us a force of 1.6 kilonewtons acting on the far end of this beam at FB. So a real world example for this would be a forklift. So we have a forklift here, and it has a distance of, on the forklift, the thing it needs to actually lift up the crate is going to be 1.5 meters, and you have a 200 kilogram crate. You're going to need to find the distributed load over this crate in order to know where this force is acting. So it's going to be halfway here. So it's going to be 1.5 over 2. And then to do that, then you're going to know how much force you need over here at the arm to lift this crate up. And if you didn't have a distributed loading, you wouldn't be able to do that. Thanks.